Well, no, that's where Parker's saying where on the planet Earth is 9.81 meters per second squared, the acceleration due to gravity. Because as you get further from the center of the Earth, gravity, the acceleration due to gravity decreases. We're pretty close to sea level here in Maryland.
Yeah.
But really, you've got to go to
a lot of places it's under.
Yeah, you've got to go to like the top of Mount Everest to be able to even measure the difference very easily. And even there, it only goes down to like 9.6, I think, if you're way up in the mountains.
Mountains are scary.
Yeah.
A lot.
Anyway, force equals mass times... But, Janan, keep asking questions like that. Okay? Mass, how did Ramsey put it yesterday? The amount of crap of it that there is. Something, I mean, that's about as good a definition as I've heard. How much matter you're made of. How much of you there are. Weight is the interaction.
How much of you there are?
Yeah, how much, I know, it's really confusing. Weight is the actual force between you and the Earth. How much is the Earth pulling you down? Now, and the problem is, again, metric, a lot of people use kilograms. They say, oh, this weighs 5 kilograms.
No, it masses.
No, it doesn't. It possesses 5 kilograms of mass. It weighs, on this planet, 40 newtons. So what's gravity on this planet? If there's 40 newtons of force exerted by this item, this rock, then, as Connor pointed out, the force is the same as the weight, 40.0 newtons. I left out the .0 there, bad significant digits me, times 5.0 kilograms times acceleration. Remember, newtons is kilograms times meters over seconds squared.
8.
Yep, so your acceleration on this planet is 8.0.
That doesn't matter, does it?
No, not for this problem, but it's just interesting that this is a planet with gravity pretty close to Earth. But this is, mainly I'm going over this, Sasha, to point out that, like, how fast the acceleration due to gravity is determines your actual weight, not your mass.
Hypothetically speaking, if someone tells me they weigh something in kilograms, I can laugh.
You, not even hypothetically, you can, yes.
And then I would just multiply it by 9.81.
And say, no, 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 this is your weight in newtons.
And then they'd seem extremely fat.
Yeah, newtons seem huge compared to pounds. Slugs are the flattering way to go. I weigh 6.25 slugs.
Yeah, but you sound like a freak.
Yeah,
well, they know what slugs are.
No, but you say slugs, then you think
I know.
Fat little...
Yeah, slugs is really not something you want to
It
talk
takes
about.
6.25 giant slugs to weigh me.
That's right. All right, now let's get to the actual question. If the astronaut exerts an upward force of 46.2 newtons on the rock, what is its acceleration? Nikki, you had this illustration perfectly. Here's the rock.
Wait, what does that say at the bottom? I can't see. It says 8. What?
8 meters per second squared. Okay, now, the rock has a downward force on it of 40.0 newtons.
Now draw whiskers.
No. And you're told that the astronaut pushes up, shh, guys, at 46.2 newtons. And the question is, how fast is the rock accelerating because of this?
Don't you multiply the weight times the... Wait, is...
You multiply the mass times the acceleration to get the force.
6.2.
Wait, is it already falling down?
It's always falling down. Gravity is always pulling that much down on it.
No, you said that weight is the mass.
Weight is the acceleration.
The acceleration. Wait, I'm sorry. No, never mind.
Okay. All right, so guys, listen up. If this rock is being pulled by gravity downward with a force of 40 newtons, and you're pushing up on it with 46.2 newtons.
Accelerating at 6.2.
Yeah, then the final force on the rock is just this 6.2 newtons of force. Now the question is, what acceleration will that translate into? Well, this is where you pull out your F equals ma, and the final force on the rock is just this 6.20 newtons. I've got to be more careful with my significant digits.
Why can't you do 46.2?
You want me to click correcting you again?
Because it's the final force. Well, because in this case, what I'm leaving out for notation is this F is the sum of all forces. Okay, because I mean, this 46.2 newtons has to overcome that 40 newtons. Because, sweetie, if this thing weighs...
So it's not going at 9 meters per second.
No. Because if this thing weighs 40 newtons, and you only push up with 30 newtons of force, what's it doing?
Still going down.
Yeah, it's falling. It's falling if you do that. You have to push with 40 newtons just to hold it still. Just to hold it up. Of course, that's not as big as it sounds. I weigh 890 newtons, apparently. So. Okay, so...
Do your work.
All right, guys. Shh. Hey. So 6.20 newtons equals 5.00 kilograms times A. So this rock is moving upwards in your hand, or your hand is moving this rock upwards. And I'm going to write out the units here. 6.20 kilogram meters per second squared divided by 5.00 kilograms. Kilograms will cancel from both, so I'm left with acceleration. That's good. And what do I get here? What is 6.20 divided by 5? 1.24. So this is moving up at 1.24 meters per second squared. Sasha, your answer of 9 point whatever that you got, that would be assuming the rock was like weightless, or that the total force on it was 46.2, but it's not. You got to subtract the weight.
Wait. I thought you said the question was you were jumping off something.
No, this is just lifting a rock.
Okay.
Problem just said the rock weighs 40 newtons, and you're pushing up on it with 46.2 newtons.
When you just explained it there, for some reason I thought rock's falling, you're on top of it, and you're jumping off of it. So,
You're thinking about that, how do you survive an elevator crash? Urban legend.
which is you go as close to the ground as possible.
Yeah, it's not that you jump right before it
No, as
hits.
soon as you jump, the top is going to crash down and crush your head.
Yes.
So
Okay.
You hold yourself on the floor.
Might be a problem on a test
Have
suit.
fun editing that out.
Any questions on... Okay, guys, any questions on number 3? Any questions on number 2 before we go on to number 3? I'm sorry. You guys good? Going once? Going twice?
Do you know the answer so you can say it beforehand so I can know if I get it right?
Nope, I like having the suspense.
Spread out.
I like having you wonder till the last second. Number 3. Number 3. Okay, listen carefully. In a grocery store, you push a 12.3 kilogram shopping cart with a force of 10.1 newtons. If the cart starts at rest, how far does it move in 2.50 seconds? Okay, so this is one of the ones where you have to remember stuff from last semester. The mass is 12.3 kilograms. The force is 10.1 newtons, which means we can right away from here find the acceleration, correct?
Yeah.
Well, you said 12.1, but you put up 10.
My apologies. It is 10.1 newtons. Thank you, and please double check me on that. So 10.1 newtons equals 12.3 kilograms times acceleration. Is that F equals ma?
Yeah.
Am I speaking clearly enough for you, Parker? All right. So now to find the acceleration,